the MIT 2024 Integration Bee Semifinals. It had two problem sets, in other words, semifinal number one, semifinal number two. So under semifinal number one, we had problem one, problem two, problem three, problem four, and then the contestants had to go into a tiebreaker series. So there was tiebreaker number one, tiebreaker number two, and that concluded that session of the semifinal. Then for semifinal number two, or the second session, it was problem number one, problem number two, problem number three, only up to problem number four. So today we are going to focus on these problems. We'll propose to you our version of the solutions. If you do have a question, please feel free to leave a comment in the comment section. If you do have alternative solutions to what we propose, please do share with us. We are here to learn and help each other out. But also, if you've not subscribed to our channel, we do really encourage you to subscribe to our channel. And yeah, that will give us that extra visibility that we need to keep growing as a channel. On to problem one of the semifinal number one of the MIT 2024 Integration Bee is the integration from x tending to negative infinity to x tending to positive infinity of x cubed minus 4x close bracket times sine x plus open bracket 3x squared minus 4 times cosine x, all that over open bracket x cubed minus 4x close bracket squared plus cos x squared. I would personally attack it. So first, I would divide both the numerator and the denominator by cosine squared x. And what that essentially leads to is a 1 plus something squared. And when I see a 1 plus something squared in the denominator, the obvious thing that I personally am inclined to do is substitute that value that is squared in the denominator with a u and then eventually tangent. But today we'll take a shorter route because we know for sure that the integration of 1 over x squared plus 1 is arctangent of x. So we're going to move towards that direction. So as you can see, after dividing by x cosine squared x, now we have x cubed minus 4x times tangent x secant x plus 3x squared minus 4 times secant squared x. And as you can see, this value in the denominator that we obviously divide whatever we've said is x cubed minus 4x secant x squared plus x. And whatever the denominator is a derivative of this value. So what we're going to do just creatively, we're just going to say, let's ignore the limits for now. And we say, hey, let u be equal to x cubed minus 4x secant x. And so du dx is equals to x cubed minus 4x tangent x secant x plus 3x squared minus 4 secant x. And so essentially what this is telling us, if you have substituted with u, du can be used to replace x cubed minus 4x tangent x secant x plus 3x squared minus 4 secant x dx. And then, so essentially our integration, the indefinite integration where we've ignored the limits for now, is equal to, in place of the entire numerator and times this dx is du. And then in place of this component in the denominator, we have u, and so u squared. And as we know, we don't want to really go further into explaining how this now comes to arctangent of u plus c. But that's the integration in the U domain. But since we know that U is equals to x cubed minus 4x second x, we can say now that our indefinite integral, ignoring the limits, is equal to the arctangent of, in bracket, x cubed minus 4x, close bracket, times second x, obviously plus the integration constant. So that now when we bring in the limits, our integration now becomes as follows, because now we have a arctangent x cubed minus 4x times second x times second x, now from negative infinity to positive infinity. There are a lot of discontinuities in this function here, and that's what we have to be really cognizant about. And as I began showing you, is that the function arctangent of x, as it's shown here, it quickly tends to pi over 2 as x decreases towards negative infinity and as it moves from 0 to positive infinity. So quickly things go towards arctangent, towards pi over 2 and negative pi over 2. In the negative direction, positive pi over 2 in the when x goes in the positive direction. So we now know that. And then we have x cubed minus 4x second x. How does this function behave? As we can see, for x cubed minus 4x, it rapidly tends to negative infinity. And then also as you move away, so it crosses x at x equals to 2, negative 2, and 0, and x equals to positive 2. And rapidly goes to positive infinity as the x goes to the positive direction. Then second x is just this up and down flip-flopping of this U-shaped curve. So when we multiply these two curves together, this is what we get. So this flip-flopping rapidly goes to infinity, and then the crossing of 0 happens at x equals to 2, x equals to 0, x is equals to positive 2. Now this, in the negative direction, what this arctangent of this function is going to be is it's going to tend to negative pi over 2. When the u is flipping the positive direction, is going to tend to pi over 2. And so you're going to have constant pi over 2 positive, negative pi over 2. So we're going to have that step up, negative, positive, negative, positive. And then from here now is where we're going to have a transition from positive. So here, first of all, so we're going to have a very interesting transition here as it goes towards 0. And so this is what essentially happens. So as you can see, from that positive infinity, we are seeing it go down from pi over 2 positive to negative pi over 2. And then that process repeats. The 0 crossing is maintained whenever the x cubed minus 4x second x was 0. That arctangent of 0 is going to be 0. And then the rest, we see the stepping away, like negative pi over 2, positive pi over 2. And so what we are having here now, we're going to divide this into several domains. We're going to have the domain negative pi, infinity to negative 3 pi over 2. Then we're going to have negative 3 pi over 2 to negative pi over 2. And then we're going to have the domain negative pi over 2 to pi over 2. And then from pi over 2 to 3 pi over 2. And then from 3 pi over 2 to infinity, right? So this is essentially what is happening. This is our negative 3 pi over 2. So this is where the stepping stops, and now we're having this smooth curve. And that happens all the way up to negative pi over 2. So here, since this is constant, this entire interval, there are obviously some sub-intervals here, but the integral here is 0. The integral here is obviously going to be 0. And let's not confuse it. We're not talking about the integrand as this curve, but this is whatever has been achieved after the integration. Since this minus this is going to be 0, this minus this is 0, all this is going to be 0. This here is 0, right? And our focus now will be here, here, here. And also these, since these are constants, these are going to be 0, 0, 0, right? So essentially, what happens now, we have 0, and then since at negative pi over 2, we have negative pi over 2, and then at 3 pi over 2 negative, we have positive pi over 2. So negative pi over 2 minus negative pi over 2, actually for the green one. The same thing happens here from negative pi over 2 to pi over 2. At negative pi over 2, at pi over 2, sorry, we have negative pi over 2. At negative pi over 2, we have positive pi over 2. So we have minus pi over 2 minus pi over 2. And then here as well at pi over 2, at 3 pi over 2, we have negative pi over 2. And at pi over 2, we have positive pi over 2. So negative pi over 2 minus pi over 2, minus pi over 2 is what we get. And then since the stepping disappears above, this entire thing becomes 0. So we have the result here being negative pi, negative pi, negative pi. And so we have negative pi minus pi as our answer, which is 3 pi. And that is our answer. Thank you very much for those who paid attention, who have followed along. If you have any question, you want further explanation, please don't hesitate to leave a comment in the comment section.
So on to problem number 2 of the semi-final number 1 of MIT 2024 Integration B is the integral from x equals to 0 to x tending to infinity of x times e to the power negative 2x over 1 plus e to the power negative x.
First, so how I would handle this problem first is I'll look at the denominator, and I would like to express that as a geometric progression problem. And in order to do that, I would tackle this plus as a negative negative. So we have this term 1 over 1 minus in bracket negative e to the power negative x as a progression, geometrical progression to infinity, with negative e to the power negative x as the common ratio, and initial term being 1. And so I could express this as that series, and obviously keeping all the numerators as they are. And the next thing I would do is I would then go ahead and express this negative as negative 1 to the power k. And then I would multiply the e to the power negative 2x with the e to the power negative kx. And so you have this convenient term that is e to the power minus, in bracket, k plus 2x, while maintaining this negative 1 to the power k, right? Then what follows here is, so we have now swapping around, because really the integration of a summation of components is the same as the summation of the integral of independent components. So we can sum up the result of what we get from integrating each independent component. And since this -1 to the power k is a constant, we can just pull that out, and now our focus now is integrating from x equals to 0 to infinity, x times e to the power negative, in open bracket, k plus 2x. And so as you can see here, we come up with, first of all, let me indicate here, integration by parts, where we initially have 1 over k plus 2 negative times x e to the power negative k plus 2x. Now this comes from us considering initially that this is our u and this is our dv, such that uv is, so v here is going to be this -1 over k plus 2 times e to the power negative k plus 2x. And then now we have minus, and this minus here, this becomes a plus 1 over k plus 2. And since now du here, because we need to get now v du, so we know our v, which is a product of this and that, but now du is a derivative of x, which is just going to be dx there. And so eventually now we, because when x is equals, or x tends to infinity, this exponential part tends to 0, right? And then when x is 0, this part here tends, or is equals to 0. So this time here, essentially the entire thing just tends to 0. Okay, then so we are left with now just the integral of the integral of e to the power k plus 2x, and then obviously the constants remain as we see. So going forward, we do now have another k plus 2 that emanates from integrating this, and this is arrived at as follows. So we have negative k 1 over k plus 2 e minus k plus 2x as the integral of this, and then the limits are shown here. When x tends to infinity, this part tends to 0, and then when x is 0, this part is 1. So we are left with now the summation of -1 to the power k over k plus 1 squared, multiplying this k plus 2, k plus 2. So this is where everything now starts being very interesting. So the first thing I would do is obviously I would just spell out the entire expression, and how we do that is first by assuming that, well, let k prime be equal to k plus 2, right, such that this tends to k prime, and this here tends to k prime minus 2, right? And when k is equals to 0, k prime equals to 2. And so we can now shuffle back k prime to k, so that's why we get this expression here. So just imagine k prime being what is k here. Now that's very interesting, because this is the same as -1 of the power k over -1 to the power 2. -1 to the power 2 is the same as +1. So -1 to the power k minus 2 is the same as -1 to the power k, right? And then we can now spell out everything here, and that is 1 over 2 squared when k is equals to 2, 1 over 3 squared when k equals to 3. Now because when k equals to 3, this is now going to be -1. There's a negative sign here. When k is equals to 4, since this is even, this becomes 1, so we have +1 plus 1 over 4 squared. And when k equals to 5, because this is a negative, we have -1 over 5 squared plus 1 over 6 squared minus, and so on. Now we can separate the odd from the even terms, and so we have 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared minus 1 over 3 squared. So in bracket here, 1 over 3 squared plus 1 over 5 squared, 1 over 7 squared, and so on and so on. If we pull a quarter out, this becomes 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on and so on. And this becomes 1 over 3 squared, so this just remains as it is. Then we can go ahead and now know, since we know that the summation of 1 over k squared from k equals to 1 to infinity is equals to pi squared over 6. This is the Bessel problem. This entire thing here becomes pi squared over 6 now times their quarter. So this is obviously taken care of. But this one here, now we have these odd terms. How do we solve that? So how we solve that, since we know that the even terms here amount to a quarter times the Bessel constant there, or the Bessel problem constant. So we know this is the odd terms minus the value when k equals to 1. So in order to compensate for that, so we've added 1 here and then we've subtracted 1 on this other side. So what then happens is we have a quarter times pi squared over 6 and so on and so on. But now we know that this is the even terms, and the odd terms is simply the sum, the Bessel problem minus the even terms. So that's what we've done here. Pi over 6 minus pi squared over 6 minus pi squared over 24, because this is just the even terms. So in order to be left with the odd term, this is what you're going to do. And then we've kept the minus 1 there. And so just simplifying this further, pi squared over 24 from 6 times 4 times 6 here, and then here we have pi squared over 24. Since there's a negative and negative here, when you add these together you get pi squared over 12. And then since we have pi squared over 6 here, we'll just keep the minus 6, and the minus and minus here amounts to a plus here. So pi squared over 12 minus pi squared over 6 is what we see here, and then when you perform that, this becomes negative pi squared over 12. So we have now this positive 1 minus pi squared over 12, and this is the final answer. So thank you.
Problem 3 of the semifinals number 1 of the MIT 24 Integration B is the, again, definite integral from x equals to 0 to x equals to 2 to pi over 2 of the sine of cotangent squared of x, close bracket, times sec x squared.
So first things first, what I would do with this problem here is I would like to express everything in form of tangent. So cotangent squared x is the same as 1 over tan squared x, and sec squared x is the same as 1 plus tan squared x. Then the next thing is I would say let u be equal to tan x, such that du dx is the same as sec squared x, and therefore du over sec squared x is equals to dx. And so expressing sec squared x in form of u would be, first of all, to express sec squared x as 1 plus tan squared x, and therefore that means that since u is equals to tan x, that means du over 1 plus u squared is the same as dx, or can be replaced for dx. And so looking at this expression here, in place of tan squared x, we'll plug in u squared, and then this is obviously 1 plus u squared, but dx is the same as du plus 1, du over 1 plus u squared. So what we see here essentially is that this 1 plus u squared and this 1 plus u squared cancel out. One thing to note is that when x is 0, tangent of tangent of 0 is 0, so in other words u is 0, as we can see here. When x is pi over 2, tangent of pi over 2 means that u tends to infinity, as we see here. So essentially we are left with an integral from u equals to 0 to u tending to infinity of sine of 1 over u squared. Very, very interesting problem. So this is where now things begin to become a little bit interesting. So the first thing that I would do is I would say let v be equal to 1 over u, such that dv du is 1 over u squared, and therefore dv du is the same as, since v is the same as 1 over u squared, so dv du is the same as negative v squared, right? And so we can bring this down here such that negative dv over v squared is the same as du, right? Now, as obviously when u equals to 0, v tends to infinity, and then when u tends to infinity, v equals to 0. And so keeping this negative sign in place, 1 over u squared is v squared, and then du becomes negative dv squared, negative dv over v squared, and then it results in this negative sign. Now, as it's known with many integration approaches, when you have a negative sign here, you can negate that by simply flipping the interval. And so now integrating from v equals to 0 to infinity, and then looking at this 1 over v squared. 1 over v squared is the same as the derivative of negative 1 over v. And so we're going to approach this as a partial, maybe integration by part problem. And how I would see that is this here is the same as du, and this here is the same as v, right? So now uv becomes negative 1 over v sine v squared, and since we have this negative here, now minus this becomes plus, and next we have 1 over v squared, 1 over v, and then the derivative dv is 2v cosine v squared. And as you can see, this and that cancel. And then the problem is, how do we approach this result here? Now, when v tends to infinity, this term here tends to 0, right? And then when v is 0, sine of v squared tends to 0. So this term here just goes to 0 at both intervals. And so we are left with now twice the integral of cosine v squared from v equals to 0 to infinity. Now this is the same as the real part of twice the integral of e to the power negative I v squared, since e to the power negative v squared is the same as cosine of v squared minus I sine of v squared, right? So and this is the real part, this is the real part, and this is the imaginary part. Okay, so we are focused on the real part. So we can integrate this entire thing and then just pick out the real part. Now, what is interesting here is that now, since this is symmetrical about v equals to 0, if we take the entire thing from v tending to negative infinity to infinity, then this is just half of that. So we've introduced the constant half here, and this cancels with that. So we are left with the integral, the real part of the integral from negative infinity to infinity of e to the power negative I v squared. Now, using Gaussian integral, we know that when you integrate this is a general thing that everyone knows. When you're integrating e to the power negative x squared from negative infinity to positive to infinity, you have the square root of pi over a. And here our a tends to be I, so our answer here is pi over I square root. And then we want the real part of that. So I is, we can separate these things a little bit. Now, 1 over square root of I square root of I is the same as essentially square root of pi times I to the power negative a half. And I is the same as e to the power I pi over 2, since this becomes cosine pi over 2, plus I sine pi over 2. Sine pi over 2 is 1, so you have I. And now, so we have everything in I here encapsulated in this. And now we can multiply the powers, so that now we get the real part of square root of pi times e to the power negative I pi over 4. So this 2 and 2, 4, and then the sign comes in here. So this, using Euler's expression, we get square root of pi into bracket cosine of pi over 4, which is 1 over root 2, minus I 1 over root 2. And as we can see, the real part is just this part, which is square root of pi over square root of 2, which is the same as square root of pi over 2. And that, my friends, is the answer that was provided. I hope who
Problem 4 of the semifinal number 1, MIT 2024 Integration B, was the indefinite integral of the hyperbolic cosine 3x squared times the hyperbolic tangent of 2x.
To this problem. So one thing that I would like to remind our viewers is that a hyperbolic cosine or cosh x is the same as e to the power x plus e to the power minus x over 2, such that cosh 3x is the same as e to the power 3x plus e to the power negative 3x over 2. Now, if we're now squaring cosh 3x, that means that we have e to the power 3x plus e to the power minus 3x over 2 squared. That becomes a quarter of e to the power 6x plus 2 plus e to the power negative 6x. And so if you separate e to the power 6x and e to the power negative 6x, bind that together and divide by 2. And then this 2 is divided by 2, so that we're left with a half outside here. We now get a representation of cosh 6x plus 1. So a half cosh 6x plus 1 is the same as cosh squared 3x. So we can now bring this into our integration. So integration of cosh squared 3x tangent or hyperbolic tangent 2x is the same as integration of a half into brackets cosh 6x plus 1 times hyperbolic tangent of 2x. So that eventually now we have pulling the constant half out, we have a half times the integration of cosh 6x times this multiplied by this, right? And then this multiplied by this. So we have cos 6x times hyperbolic tangent 2x plus the integration of hyperbolic tangent 2x. So we can now separate this into two separate integrals such that when we expand the hyperbolic tangent of 2x, which is hyperbolic sine of 2x or sinh 2x over cos 2x plus half of the integration of sinh 2x over cos 2x. And now next thing is we can just punch the cos 6x and sinh 2x in the numerator and cos 2x in the denominator for the first integral. And then now as we see here, sinh 2x is the same as half the derivative of cos 2x. So in the numerator, we have half times the derivative of the denominator. And we're going to see there's a reason that I have expressed it this way. We'll see why I'm doing that. Now I've separated this into two separate integrals. We have the blue integral and then we have the green integral. So going forward, cos 6x sinh 2x is going to play around here. So cos 6x is the same as e to the power 6x plus e to the power negative 6x over 2, and sinh 2x is the same as e to the power 2x minus e to the power negative 2x over 2. So when you multiply those together, we have this times this, we have e to the power 8x, and then this times this, we have e to the power negative, this times this is the same as e to the power negative 4x. And then going to the negative side, this times this, we have minus e to the power 4x, and then this times this, the power is the same as minus e to the power negative 8x. So we can bunch these and this, and then we can bunch this and this, right? So that we do have now e to the power 8x minus e to the power negative 8x minus brackets e to the power 4x minus e to the power negative 4x, all divided by 4. So we can now separate that by pulling half out, and then each part here is divided by 2, so that we see here we have sinh 8x, and then here we have sinh 4x. So this cos 6x sinh 2x is the same as half sinh 8x minus sinh 4x. So plugging that in to our integral, in place of cos 6x and sinh 2x, we have half of sinh 8x minus sinh 4x, and then keeping the denominator as it is. What that means is that we have a quarter, because this half goes out, we have a quarter of 2 sinh we have sinh 8x minus sinh 4x. Now, I won't go into the details, but sinh 8x is the same as twice sinh 4x cos 4x, and sinh 2x is the same as 2 sinh 2x cos 2x. And now the sinh 4x can be further expanded as shown here, which now means that the expression here is the same as 4 sinh 2x cos 2x cos 4x minus 2 sinh 2x cos 2x. Now this and that, apologies, the rest is, but we are meant to divide this. So these two cancel, so the denominator disappears, and now we have a quarter times the integral of 4 sinh 2x cos 4x minus 2 sinh 2x. And then obviously the green integral remains as it is. Now since 2x cos 2x cos 4x is the same as e to the power 2x minus e to the power negative 2x over 2 times e to the power 4x plus e to the power negative 4x over 2. And so when you multiply that together, we have this times this, we have e to the power 6x, and then this times this, we have e to the power negative 2x. This times this is negative minus e to the power 2x. And then this times this is same as e minus e to the power negative 6x. So we can bunch that, and then that can also be separated out. And so we have half e to the power 6x minus e to the power negative 6x divided by 2 minus, in bracket, e to the power 2x minus e to the power negative 2x over 2. So we see here we have sinh half times sinh 6x minus sinh 2x. So we can now take this and plug it in place of this expression here. So that means that we have, in place of this, we have 4 times a half sinh 6x minus sinh 2x minus 2 sinh 2x for the blue. And then the green remains the same. So what you can see here is divided by 2 is 2, divided by 2 is 1. And so we have a quarter times the integral of 2 sinh 6x minus 2 sinh 2x minus 2 sinh 2x. And then the green integral remains as it is. So we have a quarter times the integral of 2 sinh 6x minus 4 sinh x, branching this and this. So these are readily integratable expression, and then this half here now multiplied by this half here means that this is a quarter. Now this here definitely is the same as, because the derivative of cos 6x is the same as 1 over 6 sinh 6x. Now we have this, now we go backwards, and so we have a half, because it's 2 and it's 4 results. 2 times a quarter is a half. And then we have 1 over 6 cos 6x. And then we have this 4 and 4. 4 times a quarter becomes 1. So now we have just this to integrate, which is minus a half cos 2x plus a quarter. Since this is the numerator here is the derivative of the denominator, this becomes natural logarithm of cos 2x plus the integration constant, right? Now we can simplify this further, and we say that that is 1 over 12 cos 6x minus a half cos 2x plus a quarter, natural logarithm of cos 2x plus the integration constant c. So this is the answer. It's been enough.
So on to the tiebreakers of semifinals number 1. So problem number 1 of that tiebreaker series, MIT 2024 Integration Bee Semifinals number 1, is the indefinite integral of sec or secant x to the power 5.
So how would we solve this problem? Secant to the power 5 of x. First of all, I think what could be of interest is when you look at secant to the power 5x, if you differentiate tan x, for example, you get sec squared x. Now that times sec cube x becomes sec the power 5x. So that kind of is a hint. So how I would begin the process is I would differentiate the product of sec cube x and tan x, where you have, obviously you differentiate one component, and then you add the product of the other component differentiated. Okay. So for example, here we have would have tan x, the derivative of sec cube x, plus sec cube x plus derivative of tan x. And this becomes tan x 3 sec squared x times the derivative of sec x, which is going to be, we're going to find out that later. And then here we have sec cube x times as sec squared x, which is the derivative of tan x. And so sec x, when you differentiate, is sec x tan x. So eventually we have 3 sec cube x times tan squared x plus sec to the power 5x. What this means is that when you're integrating sec to the power 5x, that's the same as the integration of the derivative of sec cube x tan x minus the integral of this component, right? So since we're integrating the derivative of this, that is the same as just sec cube x tan x minus 3 sec cube x tan x squared, right? So this here is obviously a move in the right direction. And then now we know what tan squared x is. Tan squared x is the same as sec squared x minus 1. So if we substitute for tan squared x with sec squared x minus 1, what we get essentially is sec cube x tan x minus 3 sec to the power 5x minus sec cube x. Now this here, the entire integration is the same as what we have on our left-hand side. So we can just move this by adding 3, the integral of sec to the power 5x on both sides. So we get 4, 3 plus 4, 1 here, we get 4. The integration of sec to the power 5x being equal to sec cube x tan x plus, because we have this negative and this negative here, plus 3 sec cube x. Okay, we're progressing. Then the next stage is obviously we can divide both sides by 4 so that we remove that constant on the left-hand side. And so we have the integral of sec to the power 5x being equal to a quarter sec cube x times tan x plus 3 over 4, the integral of sec cube x. Now, our focus now is going to shift here. Sec cube x integral or integrated is the same as sec x times sec squared x. Now, sec squared x is the same as tan squared x. This here is plus 1 here. Sincere apologies. So we have the integral of sec squared, sec x tan squared x plus the integral of sec x. And now, again, we have to focus here. This part here, we're going to try to do some little acrobatics here. So the derivative of sec x tan x, since we see this squared here, if we try to differentiate sec x tan x, it's the same process. It's the same as sec x times the derivative of tan x plus tan x times the derivative of sec x. And so we have sec x times sec squared x, which is the derivative of tan x, plus tan x. When you differentiate sec x, we get sec x tan x. So we get sec cube x plus tan squared x times sec x, which is very similar to what we have here. Now, when we integrate tan squared x sec x, in other words, when we integrate this, the same as the integral of what we have on the left-hand side here, the derivative of sec x tan x minus the integral of sec cube x. And so since this is the integral of a derivative, we just get the same thing as sec x tan x here minus the integral of sec cube x. Now, if we plug this here, we get sec tan x here minus sec cube x we say this was plus the integral of sec x. Now this here is the same as what we have on the left-hand side. So when you bunch things together, we get 2. The integral of sec cube x is equals to this sec x tan x plus the integral of sec x. Okay, so we're making progress. Now we're going to divide both sides by 2 to remove this 2 on the left-hand side. We again say this was plus. Now, the integral of sec cube x now is the same as half sec x tan x plus a half sec x. Now, since we know that the integral of sec to the power 5x is equals to a quarter sec cube x tan x plus 3/4 the integral of sec cube x, we can now plug everything here into what we have here, the green, right? And so we have sec to the power 5x integral being equal to a quarter sec cube x tan x plus 3/4 a half sec x tan x plus a half the integral of sec x. And so we have a quarter sec cube x tan x plus 3/8 sec x tan x plus 3/8 the integral of sec x. And this is now what we're going to focus on right now. For me, I really enjoy integrating sec x. So this is also going to be really, really fun. So let's see. Sec x integral is the same as 1/cosine x. Now cosine x using the half angle formalism is the same as cosine squared x/2 minus sine squared x/2. Now, the interesting thing is, since this is the difference of 2 squares, this is the same as cosine x/2 minus sine x/2 times cosine x/2 plus sine x/2. And so we can also add a constant half here so that we keep constant 2 in the numerator. Now, this is the same as twice cosine squared x/2 plus sine squared x/2, so that this is 1. And then obviously distribute the constant 2 across, so it's 2 cosine squared x/2 plus 2 sine squared x/2. And now, because we have a 0 here, we could say this is the same as minus 2 sine x/2 cosine x/2 plus 2 sine x/2, so that this would cancel and get a 0. And then obviously the identity of this plus this being equal to 1, and then times 2, we get back this 2. So just doing some acrobatics here. And so we have a half, and then we can bunch the first cosine squared x plus sine squared x/2 with the plus 2 sine x/2 times cosine x/2, and then plus the second cosine x squared x/2 plus sine squared x/2. Then we bring the minus 2 sine x/2. Now, this is interesting. So we can now distribute things in the numerator, because this is the same as cosine x/2 plus sine x/2 squared. So just, and then this is the same as cosine x/2 minus sine x/2 squared, right? Now we can just split that numerator so that we have this first half with the same denominator, the second half with the same denominator. Okay, so what we're going to see here eventually is that this cancels out with this. And then what happens here is that since we have cosine x/2 minus sine x/2 twice, so this would cancel out with this, right? And so here we are left with half the integral of cosine x/2 plus sine x/2 over cosine x/2 minus sine x/2. And then here we have cosine x/2 minus sine x/2 over cosine x/2 plus sine x/2 integral. So as you can see, we're going to play a little bit farther here. this numerator on the first integral here is the same as negative twice the derivative of the denominator, right? Because when you differentiate cosine x over 2, we get negative a half sine x over 2. And then, I mean, when you differentiate this denominator, cosine x over 2 differentiated is the same as negative a half sine x over 2. And then you differentiate this is the same as negative cosine x over 2 times a half. So essentially just the same thing you have in the numerator, but multiplied by 2 and then also times negative 1. So essentially now we have a half the integral of negative 2, the derivative of cosine x over 2 minus sine x over 2 over our same denominator. And then here, as you can see, the numerator is the same as just twice the derivative of the denominator, right? Because this negative sine x over 2 comes from differentiating this cosine x over 2, then multiply by 2. And then when you differentiate sine x over 2, since the sign doesn't change, it just becomes cosine x over 2, but obviously multiplied by 2. So what we see here is that now we can use the natural logarithm. So this is a half negative 2 natural logarithm of cosine x over 2 minus sine x over 2 plus cosine x over 2 plus 2 natural logarithm of cosine x over 2 plus sine x over 2, and then obviously integration constant. So this half here goes with that and that. And then obviously using the rules of logarithm, when you have a minus, you definitely divide whatever is under the log function. So we have cosine x over 2 plus sine x over 2 divided by this cosine x over 2 minus sine x over 2. Next thing is I would like to just multiply both the numerator and denominator with cosine x over 2 plus sine x over 2. So when you do that, just multiplying by the same thing so that this would cancel out, but still giving you the same thing. So what this leads to is cosine squared x over 2 plus 2 sine x cosine x over 2 plus sine squared x over 2 divided by cosine squared x over 2 minus sine squared x over 2, because this is just the difference of squares, two squares. Then bunching this and this becomes 1, obviously. Just bunch them together, the famous identity. And then 2 sine x over 2 cosine x over 2, this is the same as sine x, right? And this here is the same as cosine x, right? So when you simplify things, you get 1 plus sine x over cosine x. And so you divide this numerator's components independently. We get sec x plus tan x, and then the integration constant. Now, since we know that the integral of sec to the power 5x is the same as a quarter sec cube x tan x plus 3 over 8 sec x tan x plus, remember this is 3 over 8, the integral of sec x, we would say then, by plugging in what we found as the integral of sec x, that the integral of sec to the power 5x is a quarter sec x tan x plus 3 over 8 sec x tan x plus 3 over 8 natural logarithm of sec x plus tan x, and then the integration constant. So my friends, thank you so much for hanging out with me in this quest for such a wonderful answer. I hope you had fun following along.
So problem number 2 in the tiebreakers of the MIT 2024 Integration Bee Semifinals number 1 was the definite integral from x tending to negative infinity to x tending to positive infinity of the hyperbolic secant of 2x plus 1 minus 1 over x minus 1 minus 2 over x plus 1. So when we have this problem, we are going to use what is called the Glasser's master theorem, which states that if you have a, ai, and bi that are real numbers, and then we have an expression u which equals to the variable x minus the real number a minus the summation of the absolute values of a n over x minus b n. In fact, I would like to convert this to I and this to I, right? And this is I. So the index is I because we stated this to be i's, right? So if you have a summation of absolute values of a, I over x minus bi, such that that summation starts from I equals to 1 to n, as capital N, then the Cauchy principal value of the integral of a function of fu equals to the principal value or the Cauchy principal value of the integral of fx, and that is from x, and not here, it's dx here, it is not du. So the expression u is just an encapsulation, it's an abstraction of what would be within the function f. And so if we have this expression here, we can create an abstraction such that we have hyperbolic secant of 2x plus a half minus a half over x minus 1 minus 1 over x plus 1, such that this here is our negative a, and this here is our absolute value of a1, absolute value of a2, this here is b1, plus 1 is b2. So, and this is exactly what we see here, right? So it's an abstraction. We're trying to simplify the function under the integral sign such that it's more tractable. What that tells us is that the integral of the hyperbolic secant of 2x plus 1 minus 1 over x minus 1 minus 2 over x plus 1, having expressed it this way, is the same as with the principal value being taken into consideration, is the same as the hyperbolic secant of 2x. That's from x tending to negative infinity to x tending to positive infinity. So secant is obviously, hyperbolic secant is obviously 1 over cos 2x, or hyperbolic cosine 2x, and hyperbolic cosine 2x is the same as e to the power 2x plus e to the power negative 2x over 2. We can flip whatever is in the denominator of the denominator there, such that 2 comes up here. And then since this is 1 over e to the power 2x, by multiplying both the numerator and denominator by e to the power 2x, that results into the integral of 2 e to the power 2x over e to the power 4x plus 1. So if we let u to be equal to 2x And then the derivative of that du dx is the same as 2e to the power 2x. And so du can be substituted for 2e to the power 2x dx. Now, the limits here, using this as x tends to negative infinity, u would tend to e to the power negative infinity, which is 0. So the lower bound here would tend to 0, and the upper bound would still tend to positive infinity. So this integral here with the substitution is now can be equated to the integral from u equals to 0 to u tending to positive infinity of d of 1 over u squared plus 1. So this is a more doable problem now. The integral of 1 over u squared is the arctangent of u. So with the limits applied appropriately, as u tends to positive infinity, the arctangent of u would tend to pi over 2. As u tends to 0, or when u is equal to 0, the arctangent of u will be 0. So the answer that we've been looking for is pi over 2. So the main thing that was required for this problem was knowledge of Glasser's master theorem, which is not really a basic theorem that you'd learn in calculus class, but with that knowledge, it seemed very easy to now transform the integral into a more tractable and solvable problem. It was an absolute pleasure solving this problem. Until now. So on to problem number 1 of the semifinals number 2 of the MIT 2024 Integration B, which is the definite integral from x equals to 0 to x tending to positive infinity of sine x times sine 2x times sine 3x all over x to the power 3.
So what happens to this problem is the first thing I would like to look at is the integral of sine ax over sine cube, because we do have these constants here. There's a reason I'm interested in integrating this. This problem is very similar to the integral of half the product of the derivative of negative 1 over x squared times sine ax. So the derivative of negative 1 over x squared is twice 1 over x cubed. But now to negate that 2, we have multiplied by a half here. Now using integration by parts, where we say if you have u dv as your problem, the integration of that is the same as u v minus the integral of v du. Now for this problem, we'll say that maybe our dv is this initial derivative and our u is sine x. Therefore, uv is the same as a half times negative 1 over x squared times sine x, and then minus v v definitely would be a half of negative 1 over x squared, and du would be the derivative of sine x. So going forward to do it, we've seen our uv is a half times negative 1 over x squared sine x, and then minus a cosine x is going to be our du, and then a half 1 over x squared is going to be over v. And that negative is negated with this negative, so we have a positive here. As you can see here, the interesting thing is the upper limit when x tends to infinity, these parts here tends to 0, so this entire expression goes to 0. When x tends to 0, or when x equals to 0, this part tends to 0, and the entire thing goes to 0. So essentially, this entire expression here goes to 0. And we are left with just a over 2, the integral from x equals to 0 to infinity of cosine ax over x squared. So this equals to this. Now, picking our problem here, sine x, sine 2x, sine 3x over x cubed is the same as we're going to try and expand this into single trigonometric function expression. So we have sine x. Sine 2x times sine 3x is going to be the difference between cosine x and cosine 5x. The difference between this and the sum of that. And then obviously divided by 2 times a half here. So going forward, now multiplying sine x across, so we have half cosine x sine x here, and the minus cosine 5x sine x over x cubed. Now this here is the same as, since sine 2x is the same as 2 cosine x sine x, or 2 sine x cosine x. So this here is the same as half sine 2x. And then here, this is the same as the difference between sine 6x, the sum of this, and sine 4x, the difference of this. So pulling half out from here and here, we get a quarter. We have sine 2x plus this negative, and negative here makes this a positive. So we have sine 4x minus this sine 6x over x cubed. Very interesting. So we do have now an expression where we have sine 2x over x cubed, sine 4x over x cubed, sine 6x over x cubed. So we can now use, since we say that the integral of sine ax over x cubed is equals to a over 2, the integral from x equals 0 to infinity of cosine x over x squared. So we can use this to replace whatever we see here. So therefore, a quarter sine 2x plus sine 4x minus sine 6x over x cubed is equal to 1 over 8 coming from this extra half here times a quarter. The integral from x equals 0 to infinity of cosine 2x, 8 times cosine x is 2 cosine 2x. Cosine 4x, we have 8 times cosine ax, which is 4 cosine 4x. Cosine 6x, 8 times cosine ax is the same as 6 cosine 6x. So this is where things begin to become a little bit interesting. This expression is also the same as 1 over x squared is the same as the derivative of negative 1 over x times, obviously now, what we have in the numerator. Using integration by parts again, so we have uv, which is the product of negative x and 2 cosine 2x plus 4 cosine 4x minus 6 cosine 6x. And then minus 1 over 8, the derivative of the numerator, which is now 4 cosine 2x, 16 sine 4x, minus 36 sine 6x. So this has become negative, has remained negative because the derivative of cosines are all negative. So when we pull the negative out, negative from this 1 over x over and the negative from the derivative of the cosine terms means that that is a positive. Okay, now interesting thing, at the upper limit when x tends to infinity, this part tends to 0. So this therefore isn't going to 0. At the lower limit when x equals to 0, this is 1. Sorry, there's a 2 here. We forgot that. So there's cosine 0 is 1, so we have 2 plus cosine 4x, it becomes 0, so 2 plus 4 minus 6, because cosine 6x is also 0 when x equals 0. So this entire thing goes to 0, from this entire component goes to 0. So this term goes to 0. And now we are left with that interesting term. So we are left with 0 minus 1 over 8, the integral of 4 sine 2x plus 16 sine 4x minus 36 sine 6x. Now, this 0 obviously is 0. Now this negative here and this negative interact, and so we have the integral for 1 over 8 times the integral from x equals 0 to infinity. Well, this becomes positive, so we have 36 sine 36, no, sine 36, sorry, sine 6x minus 4 sine 4x. Sorry. So this is sine 2x and then minus 16 sine 4x. Many apologies for this oversight. So, and since if you have sine ax over x, when you integrate that from x to 0 to infinity, and you say let u be equals to ax, definitely du is the same as a dx, and dx therefore is the same as du over a. And so in place of sine ax, we have sine u, and then in place of x, we have u over a, and then du. So this goes up, and so this and that cancel out, and so we're left with sine u over u. And then from u equals 0 to infinity, this is a very popular integration. You can use integration using the Feynman integration trick, or differentiation under the integration sign. And we know this to be pi over 2. So all these independent terms, again, as I said, this is 6x, this is 2x, apologies, this is 4x, and not that. So the constants are correct. So this is the same as 6, 2, and this is 4, right? So the constants are correct. So we can pull out the constants, and we're left with sine x over x, since we saw that if you had any constant here over x, the integral is the same as sine u over u, the integral of sine u over u, which is same as sine x over x from x equals 0 to infinity. And so that is 6 minus 4 minus 16 is the same as 16. So 16 over 8, the integral of sine x over x from x equals 0 to infinity, which is 2. Since we know this is the same as pi over 2, we have 2 times pi over 2. And so the answer is pi. So that is the answer for this problem. Kind of interesting. I hope you did enjoy.
So on to problem number 2 of the semifinals number 2, the MI24 integration B, which is the indefinite integral, open brackets, of 1 plus natural logarithm of x, close bracket, times 1, open bracket, 1 plus natural logarithm of natural logarithm of x. Interesting problem.
So the first thing I would just let u be equal to log x, such that e to the power u is x, and thus e to the power u du dx equals to 1, such that you could substitute for dx with e to the power u du. So bringing in our problem now, where you see log x, we can plug in we could plug in u, and where you see dx, we plug in e to the power u du. So this is what we've done. For this log x, we put u. For this log x here, we put u. And then for dx, we put e to the power u du. So multiplying this part together, we have 1 plus log natural logarithm of u. plus u plus u natural times natural logarithm of u, all in brackets, times e to the power u. And then now if you multiply e to the power u across, so we have e to the power u plus e to the power u natural logarithm of u plus e to the power plus u times e to the power u plus u times e to the power u times natural logarithm of u. So interestingly, there are trivial parts to this problem. What we could do initially is just to separate all these terms into separate integrals. So we have e to the power u, e to the power u natural logarithm of u times e to the power u, and u times e to the power u times natural logarithm of u. I do like color coding these problems. So we have the blue, we have the green, we have the purple, and then we do have the yellow. So the blue, which is e to the power u, is a very simple problem. So the integral of e to the power u is the same as e to the power u. And then here we're going to try and use integration by parts. So as we said, e to the power u is the same as its integral. And therefore we could say, okay, this e to the power u times natural logarithm of u is the same as the product of the derivative of e to the power u and natural logarithm of u. Same thing here. U times e to the power u is the same as the product of the derivative of e to the power u and u. And then here, u e to the power u is the same as the derivative of e to the power u times u minus 1. And then we multiply this natural logarithm of u. So using integration by parts, we know integration by parts. If you have something like that, e dv, the integral is the same as uv minus v du. Okay, so in this first instance here, we see our v is the same as e to the power u, and therefore dv is a derivative of e to the power u. Same thing here, our dv is e to the power u differentiated, and the same thing here, our v is e to the power u times u minus 1. So now what we can go next is now we can solve the green by saying that uv is the same as e to the power u log u minus the derivative of log u is 1 over u. So we have v and du is times v is e to the power u over u. And then the purple, we have u times e to the power u minus the derivative of u is 1. So we have just e to the power u. And then for the yellow, our u is going to be log u, which is here, and our v is going to be e to the power u times u minus 1. And then the derivative of log u is obviously 1 over u, and so du is 1 over u times v, which is e to the power u times u minus 1. So as you can see, e to the power u times e to the power u log u, we have this maintained here, we have this maintained here, and then kept this here, and then we've expanded this yellow part where e to the power u times u over u is same as e to the power u, and negative distress into a positive, and then we have e to the power u over u. So these two cancel out. There's a negative and there's a positive here, and so we are left with interesting integrals, simple ones. So we have this minus the integral of e to the power u, purple, minus the integral of e to the power u, yellow, and then we already have e to the power u here. So that really makes things very easy for us, because now we have e to the power u, the blue, e to the power u log u, the green, and then e to the power u times e to the power u, purple here. And then if we consider these two integrals, we realize that they are the same. So we have e to the power u here, minus e to the power u, minus e to the power u, that becomes minus. So 1 minus 1 minus 1 is same as minus 1. So we have minus e to the power u plus e to the power u log u plus u times e to the power u plus e to the power u times u minus 1 times natural logarithm of u. And since u is the same as log x, and also e to the power u being equal to x, therefore, or thereby, it means therefore that our initial problem now is equal to, in place of e to the power u, negative e to the power u, we have x, or we have minus x. In place of e to the power u log u, we have x times log u is the same as natural logarithm of x, which we put here, and u times e to the power u is, therefore e to the power u is x, and then u is log x, so we have it here. And here we have, in place of e to the power u is x, u is log x minus 1, and then log u is the same as natural logarithm of x, since u is natural logarithm of x. So we can expand whatever is in the bracket. So just simplify it a little bit more. And as you can see that this term here is the same as this term, only that the signs are flipped. So we can cancel those terms out, right? And so our final answer is going to be minus x plus x times natural logarithm of x plus x natural logarithm of x times natural logarithm of x. In fact, what you could do is this is in its own bracket, and this is in its own bracket. Yeah. Okay. So that is it. That's our final answer. Thank you so much.
On to problem number 3 of the semifinals number 2 of MIT 2024 Integration B. That is the integral from x equals to 0 to x tending to infinity of e to the power negative x squared over x squared plus half all squared.
Into the problem, the first thing that I looked at this problem and popped out was the derivative of negative 1 over x squared plus 1 over 2 is the same as 2x over x squared plus a half squared. So this part here is very similar to the denominator here. So this denominator. So our problem here can be expressed as the integral from x equals to 0 to x tending to infinity of e to the power x squared over 2x. Now this 2x is supposed to cancel this 2x times the derivative of negative 1 over x squared plus 1. And so this problem now has rendered itself interesting, because now we can look at our problem as the integral of u capital U dv being equal to uv minus the integral of capital V times capital d capital U. And so our u is this, and our v is whatever is inside the bracket, and therefore our uv is e to the power negative x squared over 2x times our v is negative 1 over x squared plus half, and therefore applying the limits appropriately. Now I'll keep it this way because it's there is a reason why I want to keep it this way, because the limit as x tends to 0 is not exactly 0, or so we want to keep it that way, so that when it interacts with the succeeding terms, the entire thing goes to 0. That's why I want to keep it that way. Now v is negative 1 over x squared plus a half, and then du is the derivative of e to the power negative x squared over 2x. So that is that. Now going forward, we see here again we can continue with the process of integration by parts. And so as we can see here, we've kept our first term as it is here, and now this derivative here is the same as deriving this first. We can apply the derivative of a product, which we derive first of all e to the power negative x squared, which is negative 2x e to the power negative x squared, and keeping 1 over x as it is, and then we add plus the derivative of 1 over 2x, which is negative e to the power, which is 1 over x, negative 1 over 2x squared times e to the power negative x squared as it is here. Now simplifying that further, keeping this first term as it is, and then pulling out negative e squared over 2x squared out, and we're left with x squared plus a half, and this and that can cancel, so we are left with this negative and negative becoming a positive. So we have now a reduced integral, which is now e to the power x squared over x squared, integrated from x equals to 0 to x tending to infinity, which is interesting. Now going forward, what happens is that we can now consider this 1 over x squared as the derivative of a negative 1 over x, right? And so doing another integration by parts, so we have our uv, which is, we have obviously this negative as it is there. Our uv now is the product of this and this, which is e to the power negative x squared over x, 0 to x tending to infinity. And then since we have this negative here, the minus and this negative interact, so we have a plus, the derivative of e to the power negative x squared, which is negative 2x e to the power negative x squared. And as we see, this and that interact, and this and that cancel or converted to positive, and so we have now very interestingly these first parts, keeping them that way, and then we have plus 2 the integral from x equals to 0 to x tending to infinity of e to the power negative x squared. So I'd like to combine these two together, and what comes out of there is now e to the power x squared over x minus e to the power x squared over 2x times 1 over x squared plus a half, and with the limits applied appropriately, and then keeping this as it is. Simplifying this further results into now x times e to the power x squared over x squared plus a half. Now this is the same as the limit as x tends into infinity of x squared, x times e to the power negative x squared over x squared plus a half, minus the limit as x tending to 0 when of x times e to the power x squared over x squared plus a half. With this, it's very simple to see that when x is 0, this is the denominator is a half, the numerator here is 1, and this is 0, so this entire thing goes to 0 because this x here makes it collapse to 0. And keeping this as it is, we're left with now the harder part, which is looking at it when x tends to infinity, right? When x tends to infinity, it's interesting what happens there. If we separate this part here, and we have a product of limit x tending to infinity and x tending to infinity. When this, you consider this part alone, x tends to infinity, x squared plus 1 tends to infinity, so we can use L'Hopital, and with L'Hopital you get the first derivative of the numerator, which is 1, and this is 2x, So we have a 0 with this part, and then obviously this one also 0. So when x tends to infinity here, this part here tends to 0, and so we're left with twice the integral from x of x, integral from x equals to 0 to x tending to infinity of e to the power x squared. Now this is a popular Gaussian integral, and this is the positive half of a complete Gaussian curve, and it's a half of obviously the entire integral from x tending to negative infinity to x tending to infinity. And so if we apply the half cancels with these two, and so we have the full integral now from x tending to negative infinity to x tending to positive infinity of e to the power x squared. Now this here is definitely equal to the square root of pi, which is the answer for this integral. Very interesting. I hope you did enjoy following along. If you have any questions, please feel free to share it with us. We would like to hear from you. Any suggestions you may have on how we could solve this problem in a different way, we do welcome that. We're here to learn.
On to the last problem of the semifinals number 2. That's problem number 4 of that semifinals. MIT 24 integration B was the indefinite integral of tangent x times secant x squared times cosine 2x times e to the power 2 times cosine x. And that is the last problem of the series, and so we'll go and look at how to solve it.
So the first thing that we would do here is one, we would like to decompose the double angle formulation. The cosine 2x now can be decomposed to a single angle formulation, which is cosine squared x minus sine squared x. And then we'll keep the other terms as they are. And we know sec squared x is the same as 1 over cosine squared x. So when this cosine squared x gets multiplied across, that becomes tangent x times, in bracket 1 minus tan squared or tangent squared x times e to the power 2 cosine x. Now this tangent squared x can be expressed as sec squared x minus 1. So when we simplify things further, so we have tan x times in bracket 2 minus sec squared x times e to the power cosine x. Continuing further, so when we multiply tangent x across and also e to the power 2 cosine x, we have now a 2 tan x to the power tan x times e to the power 2 cosine x minus tan x times sec squared x times e to the power 2 cosine x. Now what we can see here, tangent x can also be expressed as sine x times 1 over cosine x, or 1 or sec squared sec x. So this expression 2 tan x e to the power 2x can be expressed as 2 sine x sec x times e to the power 2 cosine x. Now this term and this term here can be expressed as the derivative of negative e to the power 2 cosine x, since when we differentiate e to the power 2 cosine x, the same as e to the power cosine x times the derivative of 2 cosine x, which is negative 2 sine x. So this here can be expressed as this, and then this second term here is the same as the derivative of sec squared x. So this is very interesting. Now one important thing to note is that when you differentiate a product of two functions, u and v, then that is the same as the sum of, for example, u times the derivative of v and v times the derivative of u. All right, so we can create a scenario whereby we have this expression and this expression come to be represented as uv. So what I've done here is, since we have the derivative of negative e2 cosine x, this is the same as negative the derivative of e to the power 2 cosine x, and then we don't have derivative of sec x, we can create a phantom or an imaginary scenario where we have the product of e to the power 2 cosine x and derivative of sec x. And so we create another expression that is opposite in sign so that they could cancel out. So essentially this is 0, but we're going to make sure that this and this interact, and then the same thing we do for the second part here. So I apologize, so this is the same as a half of the derivative of sec squared x, so we've kept that there. So this is half times the derivative of sec squared x times e to the power cosine x, and then we keep that negative a half sec squared x times the derivative of e to the power cosine x, and then we have applied the same function but opposite in sign, so this and this would cancel out and take us back here. However, so we can have this and this interact, so we have a scenario where we have negative the derivative of e to the power cosine x times sec x, and then the second part here remains, and the same thing here, we have half times the derivative of e to the power cosine x sec squared x, and this last part remains. So let's continue. So what happens next is that we're going to show that this here is going to cancel out with this, and how we do that is we go ahead and expand the derivation of the derivative or differentiation of sec x. So sec x is the same as tan x sec x, and then when we differentiate e to the power 2 cosine x, this is the same as negative 2 sine x e to the power cosine x. Now sec squared x is the same as 1 over cosine x times sec x, and as we continue with our process, we see that this and here interact, so we have tan x, and this half and 2 interact, so we have a negative 1, and then we have sec x. So what this results into is a negative tan x sec x e to the power cosine x, and we see that this one here cancelled out with this, and so we are left with the integration of the derivative of e to the power negative e to the power 2 cosine x times sec x, and then minus the half the derivative of e to the power cosine x sec squared x, right? So there is a dx here. We forgot to include that. And if we're integrating the derivative of these functions, what that means is that the integration of this is just the same as these functions, right? So we have the answer being negative e to the power 2 cosine x sec x minus half e to the power 2 cosine x sec squared x. And so a more neater expression of that is negative in brackets sec x plus sec squared x over 2 times e to the power cosine x, obviously, plus the integration constant c. So this is the answer. It was interesting. Thank you so much for tuning in. We appreciate your support, our subscribers. We don't take your support for granted. For those of you who are here for the first time, haven't subscribed, please do us a favor and hit the subscription button. And for those of us who haven't yet subscribed but are here for the second or third time, we do really encourage you to consider subscribing. Until next time, bye.